So there's good news and bad news. The good news is this is the last topic of the unit. The bad news is what always follows the last topic of a unit? Unit test, coming up this Thursday, of course. The last topic is satellites, and we talk about satellites purposely last because it kind of ties together a lot of what we've done in this unit. The first thing we did was circular motion. Then we moved on to gravity. Satellites encompasses both circular motion and gravity. A satellite is defined as an object that revolves around something else. Now, normally, when something revolves around something else and we call it a satellite, it's because of gravity. So you've got an object that's moving more or less in a circle, and it's held in that circle by a centripetal force, which is caused by gravity. So we've got the beginning of the unit, the whole circular motion stuff, tied together with the last few things that we've been doing, which is the gravitational force. Now, two kinds of satellites that we talk about, and we distinguish between. There's the natural satellite and the artificial satellite. A natural satellite is something like the Earth that revolves around the sun, or the moon that revolves around the Earth. It's anything that orbits something else that we didn't put there. Now, we don't usually think of the moon as being a satellite, but because of the definition of a satellite, it is. It orbits around something else, and it does it because of gravity. Earth, same thing. Earth orbits around the sun. All the other planets, same deal. Natural satellites. Artificial satellites are things that we've put there, that human beings have put out there. Maybe a communications satellite, maybe a weather satellite, maybe a spy satellite, maybe the International Space Station that orbits around Earth. One completely natural, the other completely artificial we've put there, but the analysis of the two is exactly the same. In the end, they all experience a centripetal force, and in the end, it's always caused by the force of gravity. So in the end, what we're going to do for satellites is end up setting those two forces together. Because the centripetal force acts on an object going in a circle, and the centripetal force must be caused by something, in this case gravity, we will, as you're going to see in just a moment, set Fc equal to Fg. And that's how we're going to solve all of these satellite problems. Fc equals Fg. Just like Fc was equal to Ff for cars going around a turn, just like Fc would be equal to F electric for an electron orbiting around the nucleus. Just like Fc is equal to the force of my hand when I'm swinging the keys around my hand here. In this case, Fc is equal to Fg. Now, because this equation, as it's written here, doesn't appear on your data sheet, my suggestion is every time you see a problem involving a satellite, derive the equation like I am right now. mv squared over r equals gm1 m2 over r squared. We can simplify this. One of the r's disappears, and that happens because I can multiply both sides by whatever I want. I multiply both sides by 3,124, as long as I do it to both sides. Or I can multiply both sides by r. If I multiply both sides by r, then the one on the left side disappears, and one of the ones on the right side disappears. Now, the mass on the left side cancels it with one of these masses as well. Which one? Well, let's call m1 the mass of the satellite. Let's call m2 the mass of the producer. What mass is this over here on the left side, the satellite or the producer? The thing that's orbiting or the thing that's being orbited? The thing that's going in a circle or the thing that's being circled around? Good. So this is the mass of the satellite, the thing that's doing the orbiting. That means ms cancels, and we're left with v squared is equal to g times the mass of the producer over r. Now that allows us to solve for v or g or m or r or whatever it is that we're looking for here. Again, that equation doesn't appear on your data sheet. This one does. This one does. You just have to remember to put them both together and then cancel out things and do a little bit of manipulation to get what we got there. Let's try an example here, 5.11 on 278. It says Earth's moon is this far from the Earth. Now, they have a diagram drawn here, so that means it's this far from the center of the Earth. That's good, because that's the distance we want, to the center of the Earth. Center of the moon, center of the Earth. We want to find the orbital speed of the moon. The moon is a satellite of the Earth. So we're going to say FC is equal to FG, because that's what we do when we have a satellite. mv squared over r is equal to g m1 m2 over r squared. R's cancel. One of the masses cancel. V ends up being equal to the square root of g times m over r. What mass do I have left? The mass of the moon or the mass of the Earth? The Earth, the mass of the producer, which is the Earth here. So let's say V is equal to the square root of 6.67 times 10 to the minus 11 times the mass of the Earth, which is on your data sheet. Okay, it's not given to us here, but it's on your data sheet. 5.97 times 10 to the 24 kilograms divided by R, 3.844 times 10 to the 5 kilometers, right? Right? Yeah, it is 10 to the 5 kilometers, but do we want to put kilometers in our equation? Let's go meters. So it becomes 3.844 times 10 to the, no, other way. Other way.
There's two ways.
Yes, and you picked one way.
I said 6 and 4.
You said 7, 6, and I said the other way.
And then I said 4.
No, I know.
Wrong.
How about 8? Multiply by 1,000, right? So multiply by 10 to the 3, 10 to the 5 becomes 10 to the 8. Before we calculate that, I want you to write down on the side of your paper right now, before you calculate anything, how fast you think it's moving. Okay, what's your gut feeling? What's your best guess as to how fast the moon moves around the Earth? Okay, write that number down right now. Commit to something. And then we're going to calculate this. We're going to say 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24. Now, watch this, guys. Remember, this is inside the square root sign, so this isn't going to be my final answer. But watch where a lot of you make mistakes. Okay, I've seen this a million times over the years, and even lots of times this year. Okay, we divide that top number by the bottom number, 3.844, times 10 to the 8, right? That gives me the wrong answer. I've got to square root that, right? But even if I square root it, that still gives me the wrong answer. Why? Because my calculator assumes when I do it this way that I want to go 6.67 times 5.97 divided by 3.8 equals, and then times the whole thing by 10 to the 8. It's not what I want to do. So you get a couple of options here. You can insert some brackets here. And press equals. Or alternatively, and this is what I would prefer you do, if you do this, 3.844, second function EE, then it ties it together for you. You're telling your calculator when you do this that the exponent that you put in goes with the 3.844. It's not just a number that you're multiplying it by, it's part of the number. So I want to do 3.844 times 10 to the 8. And then I don't need to worry about brackets. Okay, it's never a bad idea to put brackets in, but it's not necessary in this case. Now remember, I'm not quite finished. Got to square root that. When I do, I get 1,017. Listen, 1,000 meters per second. That's pretty fast, eh? Let's take a look at these two questions on page 278, please. I've copied over the data table for you, so the information you need about Neptune and so on is on this data table, so you don't have to flip back and forth between the pages, right? Give it a whirl, check it over in a couple minutes here. Let's take a look at number 2 here. We got a planet, and we have a moon orbiting around that planet at a speed of 6.68 times 10 to the 3 meters per second. We want to use that speed and the mass of the planet to determine the radius of the moon's orbit. Okay, so let's set it up as a satellite problem, because that's what it is, right? When you got something orbiting around something else because of gravity, then we say FC is equal to FG. We're going to always try that. we're going to say mv squared over r is equal to gm1 m2 over r squared. One of the r's cancels. One of the m's cancels. What am I left with? V squared is equal to g times m over r. What's the m there? The mass of what? Is it the mass of the planet, or is it the mass of the moon here in this case, Dom? It's the planet. It's the producer, right? What are we looking for here? We're looking for r. So let's take the r up by multiplying, the v squared down by dividing. Gm over v squared. Okay, the mass of the planet we're given is 8.68 times 10 to the 25. And we divide that by v squared, which is 6.68 times 10 to the 3 squared. Let's do this on the calculator because it is a little bit tricky with the squared on the bottom. Go 6.67 times 10 to the minus 11 times 8.68 times 10 to the 25 divided by brackets, use those brackets, 6.68. Now again, I prefer to use the second function EE, 3 and the brackets, and square that, square everything inside the brackets, square everything on the bottom basically. We end up with, oh my goodness, 129, is that right? Is that the answer that we have there? Yeah. I'll give you a little trick here. I don't know about you, but I get nervous when I see something like that and trying to convert that to scientific notation. I get nervous that I'm going to count the decimal places wrong, and I'm going to make it like 10 to the 7 when it should be 10 to the 8 or something like that. Anybody else have the same anxiety that I do when they see that? No? Well, just in case you do, here's a little trick that I use sometimes when I see something like this. I go mode. I go down, I go over here to scientific notation, press enter, and then I just multiply that by 1. So basically I get the same number, but now it's going to be in scientific notation for me, 1.30 times 10 to the 8 meters. Now we got no chance of making a mistake with moving the decimal place. Okay, I'm not going to move it over the wrong way. I'm not going to make it 10 to the minus 8 or anything like that, guys. I'm just going to, hey, my calculator does it for me. Caitlin, question? No, we didn't have to square root it because we're looking for r. And remember, there was an r on one side and r squared on the other side. Yeah. So if you're solving for v, Caitlin, you're right. You do have to square root it because v squared is, right? But r, in the gravity equation, just pure gravity solving for r, you would have to square root it. But when you're combining the two there, one of the r's disappears, so it just becomes gm over r. Good? Okay, let's do one more example, guys, and then we'll wrap it up for the day here, okay? 15.12 on 279. Because it says Landsat is an Earth imaging satellite that takes pictures of the Earth's ozone layer and geological features. It orbits the Earth at a height of 912 kilometers. So, sounds like a lot, but really, like Vancouver is further away than this Landsat satellite is. Okay. This is twice as far, more than twice as far as the space station is above us, but it's still really not that far up. We're going to find the orbital speed and the period of orbit as well. Okay, we're going to start off by setting Fc equal to Fg, like we do when we have a satellite. And we're going to start canceling things to simplify a little bit. One of the r's disappears. One of the m's disappears. We're left with v squared is equal to g times the mass of the producer over r. Solving for v, we're going to say v is the square root of 6.67 times 10 to the minus 11 times the mass of the Earth. That's on our data sheet if you don't remember what it is. And divided by the radius here. What r do I use? I got two numbers here, right? I got 912 kilometers, and then they throw in this extra one right here, RE, 6.38 times 10 to the 6. Which one do I use? Michael? Yeah, you got to combine them, right? Because you want the distance from the center of the Earth to the satellite. And that distance is the radius of the Earth plus the distance of this satellite above the surface. So we're going to say it's 6.38 times 10 to the 6 plus 912,000 meters. Let's definitely do this one on the calculator, okay? I get 6.67 times second function EE negative 11 times 5.97 times 10 to the 24. Let's press equals on the top. Okay, we don't have to do that, but just so it doesn't get too cluttered here. Let's divide that by some brackets. 6.38 times 10 to the 6 plus 912,000. What did I do? Oh, it is. You're right. Thank you. That should be plus. Yes, you're right. Equals. That's not right. Where's the mistake here, guys? No, I didn't square root it for sure. Oh, sorry. Yeah. No, that's right. I didn't even notice the 10 to the 7 there. I'm still in scientific notation. So that number seems better, yeah. I looked at it and thought 5.46 is way too small, right? Way too small. But 5.46 times 10 to the 7 makes more sense. If I square root that, not tan it, but square root that, okay, I get 7.39 times 10 to the 3. So this guy's got to go even faster, right? 7.3, 7,400 meters per second. That's Mach 20-ish, Mach 20. That's pretty fast. 7,400 meters per second. Well, we're asked to find one more thing, the period, the time it takes the satellite to go around the Earth once. To do that, we're going to say v is equal to 2 pi r over t. Just rearrange it to solve for t. Right, swap places with the v. T goes up, v goes down. 2 times pi times, we got to use that big number for radius here, whatever that worked out to be. 912,000 plus 6.38 times 10 to the 6. And divide that by the speed of 7.39 times 10 to the 3. Okay, calculate that. I don't know what it works out to be, but you guys can manage that. How is this question different than the ones that we've been doing? Well, first of all, you were asked for two things, speed and period, whereas usually you're asked for one or the other. Second of all, what's the big difference with this question? What's the big difference here? We weren't given the distance from the center of the Earth to the satellite, and we were in all of our other questions. This time we're given the distance above the surface of the Earth to the satellite. Okay, we have to remember always that when you're dealing with gravity, you're always talking about the center of one object to the center of the other object. So if you're only given the distance from the surface, then you got to add the radius to that. That make sense? I got a question for you, just a kind of a follow-up question of this, and then I'll set you free on the practice problems there. What if this question was phrased differently? What if this question was asking you to find, given the period, given the speed, what if it asked you to find the distance above the surface? How would you do that? We won't do it, but how would you do it? If you're looking for the distance above the surface as opposed to v. Look, in the end, go ahead, Ben. Good, perfect. You'd solve for r, solve for the distance, but remember that distance was from the satellite to the center, right? So if you're looking for the distance above the surface, you would take that distance that you just found from the satellite to the center of the Earth, and then subtract from that the distance from the surface of the Earth to the center. In other words, the radius of the planet. Make sense? So don't blindly add two numbers together. Don't blindly subtract them. Sometimes the number you're given is the number you want from the center right out to the satellite. If it is, great, go with it. If it isn't, then add them. If you're looking for the distance above the surface, then be prepared to subtract. Okay, just use a little bit of logic, and generally these problems aren't so bad if you're thinking about it. All right, let's give you a couple more questions to work on, 1 and 2 on 279. See how you can do on those, and that'll be it for the day.